Okay, so at this point we have fairly rigorously built up the idea that of how we know integrals exist in Rn and regions in Rn. It's not so easy to use in practice necessarily, and so we want to go into the standard calculus 3 techniques for doing integrals this class and justify when we can use them, when we cannot use them. So this is iterated integrals. Right, and the idea is that, all right, we have techniques and tricks that work in 1D. Can we essentially reduce our higher dimensional integral to a bunch of one-dimensional problems? When can we do it? All right, so, I mean, this is a totally standard thing to maybe do, is say we have a function that we want to integrate, I'll just say over a rectangle for now. And maybe just to give it some data, this is x plus y, and R is some rectangle. All right, and what I'd really like to do is to say, well, let's treat this as an iterated integral. So I take my function. These are not the right limits, are they? Okay, I first treat x fixed, right, and integrate over the y variables. Then I get something that only depends on x, and then I integrate over the x variables. And we have tricks for doing this, of course. So the question is this integral, which we have a precise definition for, and it has nothing to do with 1D integrals, is this the same as this? And when is it the same? Or when can I change the order of integration? All these things that we want to do. So this form is called an integrated integral. So I'm going to write this up precisely, the theorem that we want to prove, and then we'll see when this works, and then we'll also see an example when this doesn't work, because it's always good to be aware of the limits of what we can do. So what we did here is we took this in pieces. We said, let's define an inner function that was, say, the integral over c to d of f with respect to y. So we computed this first, 1D integral, and then we computed another 1D integral. We said, let's integrate this function. So the question we want to ask is, can I expect that I will be equal to the integral over a rectangle of this function? And this question is answered by Fubini's theorem. All right, which I'm going to write down Fubini's theorem in the two-dimensional case. We'll prove it in the two-dimensional case. Then the jump up to higher dimensions is the same. So Fubini's theorem in the plane in 2 dimensions says this. So let's suppose that we start with a function that's integrable so that this thing actually exists. That's probably a reasonable requirement. So let's suppose that f, which takes the rectangle to the reals, is integrable on this rectangle. And I'll give this rectangle by AB cross CD. And that the building block we need for doing this iterated integral, we'll call this capital F of y, So this is going to be, we integrate away the x variable. This also exists. And it has to exist for every y, right? This is a function, so for each fixed y, we do an integral. Different y, different integral. So this exists for every y in c to d. All right, this is all we need. Basically, these building blocks to work, and we're in business. We can start breaking up our integral into little pieces. So then we can say that capital F is integrable on CD, so on this interval. And when we integrate it, we get the value that we're hoping for. So the integral of f of y, capital F of y, is equal to the integral of our original function on this rectangle. Okay, so this is the result that we expect to be true. We haven't had to assume anything too crazy. So again, let's prove that it works, do some examples, and also, again, look at the edge cases where this can break down. All right, so let's start with this object that we're after, and I'm just going to give it a name so that I don't have to write the whole integral every time. So let's call that capital I. And what do we know? Well, we know that this integral, wherever it is, here it is, this integral exists. So we can write down what that means. So the usual things that we do. We take what we're given and we write down what it means. So I know that for all epsilon greater than 0, there exists some delta greater than 0, okay, such that if P is a partition, with norm less than delta, right, then all of the Riemann sums, all of the upper sums and lower sums stay within a distance epsilon of this quantity I. Okay, so we'll write that. Here are some, I'll write it as upper and lower bounds on our upper and lower sums, but these then also apply to any Riemann sum. Okay, so we talk about the, let me finish this sentence. If P is a partition with norm less than delta, then here we have our lower sum. All right, this is close to I. We expect it to be a lower bound on I. But it's not too small. It's not way below the integral I. The most below it can be is I minus epsilon. You were getting worried that I wasn't going to put the epsilon there. I see that. All right, and then this, of course, is less than or equal to the upper sum, which is going to be less than or equal to I plus epsilon. So everything is sandwiched in here, and the Riemann sums are sandwiched in between here. So I kind of have everything I need here, and I can pick whatever pieces I want as we go along. All right, now what do we need to do? We need to also think about some one-dimensional integrals, which means I need to start partitioning CD and AB separately. That's happening inherently in a 2D partition, but we need to do it explicitly and think about also what does it mean for this guy to exist. All right, so let's choose partitions. Okay, so we'll explicitly choose these partitions of our intervals, obviously to have norm less than this delta, because this is a delta we can work with here. Okay, so let's choose partitions, P1 and P2. So P1 has this form of, it starts at A and ends at B, and P2 starts at C and ends at D. And of course, we'll choose them to have norm less than delta. And from these 1D partitions, of course, we build up a capital P that we can use in our overall two-dimensional integral. So P equals P1 cross P2. Also has norm less than delta. All right, so what are we going to do? Well, we need to do some 1D integrals. So I need to do a Riemann sum of this, essentially. I need to do Riemann sums or upper lower sums or something of this, and try to show that I can force it to be close to this quantity I. So let's write that down. So we need to do a Riemann sum of capital F of y over P2. Okay, and what we hope is to find that this is pretty close to I, as close as we want it to be. Okay, so let us do a Riemann sum. What does that mean? It means that in each of these subintervals, all right, we're on this partition. In each of these subintervals, we have to pick a reference point where we're going to evaluate our function, and then we sum all these up along with the length of the subintervals. Okay, so let's pick any A to J belonging to the appropriate jth interval. Okay, and the Riemann sum then is, we add up over all of these intervals, j equals 1 to n. All right, capital F evaluated at this reference point times the width of the subintervals. All right, and once again, our goal is to show that this quantity sigma is close to I, capital I. Well, if we're going to try to argue that, we need to figure out what's going on in here. So what I'm going to try to do is get some upper and lower bounds for whatever this quantity could be, okay? And that will in turn give me some upper and lower bounds for sigma. Hopefully those upper and lower bounds are pretty close to capital I. Okay, so let's try to bound this quantity. So let's remember what it is. This quantity also came from doing a single integral, where we integrate away the x variables. So this is f of x and a to j. Okay, so let's try to get bounds on this guy. We can, again, get bounds on this guy by thinking about upper and lower sums for this integral. Okay, so we have a partition. Now we're thinking about this partition. And we need to look at all of these subintervals. A to j is just some fixed quantity, whatever it is. We don't need to worry about that right now. Okay, so let's do the upper and lower sums of this. Okay, so we do our usual thing in each subinterval. So in the ith subinterval, we have to take the infimum. I'm going to also index this by j. Now we're only taking the infimum over the ith subinterval, but the quantity is going to depend on what this particular value of eta happens to be. So this is going to be the infimum of what? Of f of x, a to j. Again, we're only taking this infimum over the ith subinterval. A to j is just some number. Okay, this guy we know exists, so these are well-defined quantities. There's no issue there. Okay, same deal with the supremum. And now the upper sums and lower sums we get from these are going to give us upper and lower bounds for this integral, right? The upper sum is always overestimating things, so that will be an upper bound. Okay, so what do we know? We know that the upper and lower sums bound the integral, so we know that. Right, here is our lower sum. This is going to be less than the value of that integral, which we call capital F. Which is bounded, once again, by the upper sum. Right? Another way of saying this, I guess, would be that the upper sum of, the lower sum of little f of x and a to j over p1 is a bound, and the upper sum is our upper bound. Okay, so now we've got to build this up in a way that we somehow get back to Riemann sums or upper lower sums or something of our original two-dimensional integral. So these are upper and lower sums of our capital F, but let's try to relate back to an integral over our original rectangle. Right, so when we were building capital F, these were our little mj, our big mj. Now to build our original two-dimensional integral, we'll get something similar but not exactly the same, because now we're doing the infimum over these little two-dimensional boxes, not just with a fixed a to j. So I'm going to use a tilde to denote the infimum and supremum when we're trying to build upper and lower sums over our 2D rectangle. So this is the infimum of f, but now over this two-dimensional region. Right, similarly, we get a capital M. All right, so I guess one question we need to ask is, how did these quantities, well, let's just do little m to start with, how does this little m tilde relate to that little m over there? Definitions are similar, but not identical. Which one's bigger? That one is bigger, exactly, right? So this one just picks a fixed y value in our little rectangle, and then takes an infimum over x at that fixed y value. Here we're taking the infimum over all x and all y, right? Which means it's going to be less than or equal to whatever quantity we got there. So we notice this, that little m tilde is going to be less than or equal to our original m, and other way around for our capital M. Okay, so if I'm trying to take this quantity and somehow start making it look, I have to do one more Riemann sum to get the extra dimension in there, but I somehow want to get it to look like this integral over our 2D regions, what I'd really like is to get this in terms of m tildes instead of m's, because the m tildes are the things that let us now say, but these somehow give us something close to I. Now I can do that. So I can say, without messing up my inequalities, capital F is sandwiched in here. This is less than or equal to the sum with a capital M, and that's going to be less than or equal to the same sum with the capital M tilde. And same deal over here. This will be greater than or equal to the same sum with the little m tilde. Okay, so that is going to give us, I'm going to repeat this line here, but again, I get to replace these with m tildes and I don't break the inequality. So I equals 1 to m of m tilde ij xi minus 1 less than or equal to our capital F less than or equal to our sum of capital M tilde xi minus 1. All right, so where are we going? We're trying to get back to this guy, right? This was our goal. Sigma was this Riemann sum that we got by doing the iterated integrals, one dimension at a time. Okay, so I'm trying to get back to a bound on this. I want to show that this quantity is close to I. Now I'm kind of going the right direction because these are the quantities that are going to show up when I talk about capital I. Okay, so what do I need to do this? I need to take that capital F. I need to multiply it by this y spacing and sum them all up. So that's what I need to do all the way through here. Multiply by the y spacing and sum over all the j's. Okay, so from here, we're going to get a double sum now. J equals 1 to n, I equals 1 to m, m tilde, xi minus 1, yj minus 1. Is less than or equal to, do the same thing to this line. multiplied by the yj minus 1, and then do the same thing to this last line. So I get my capital M tildes. All right, what's this quantity? What's another name for this quantity? The lower sum of f over what partition? P1, which one? The whole thing, exactly. P, the two-dimensional partition. So this guy we identify as the lower sum of f over this two-dimensional partition, right? These m tildes we got, you're still here, these m tildes we got by taking the infimum over the entire little box, right? So these are the right m's, the right infimum to show up in lower sum over the big partition. This guy is precisely how we define sigma at the very beginning of our proof, and said that's the thing that we're working towards. Okay, so we were working towards it. Our goal was to get bounds. We got bounds, but then the goal was to put the bounds back in here. Now we've done that. And then on the right-hand side, we get the upper sum, again, over our full partition. But we know that because f is integrable over this 2D region, that this guy stays really close to I. We said it stays within epsilon, and this guy also stays within epsilon. So we're going to have from this that I minus epsilon is less than or equal to sigma, is less than or equal to I plus epsilon. And that's what we needed to show, right? We started with a generic partition of P1 and P2. We built up the Riemann sums that would come from the iterated integral. Okay? And we showed that, indeed, those Riemann sums always stay within a distance epsilon of I. So that is, indeed, exactly what we needed to show. Questions? Yeah?
Can you explain the relations between how we figure out that the Mij tilde is less than or equal to M?
Why do we know that the Mij tilde is less than or equal to that? So this is an infimum of the values of f everywhere over this whole rectangle. Now one of the points in this rectangle is to take y equals a to j. A to j lives in this interval, right? So the infimum, if we're taking the infimum over this rectangle, it has to be less than or equal to the value we get when y equals a to j, because that's one of the values that we're looking at. So it could be that a to j gives us our minimum, exactly. It could be that there's a minimum somewhere else, or if there's no minimum, there's just an infimum, but it will always be less than or equal to the fixed value in the rectangle. Any other questions? It goes without saying, you can swap the roles of x and y, and the theorem still holds. All right, so you're given an integral to do, and you say, oh, this would be much easier as an iterated integral. Let me build it up as an iterated integral. You do it. You get a number at the end of the day. Great, no problems. Is that equal to your original integral? So what could go wrong here? Let me ask the question this way. You do the iterated integral. So if f of y exists and is integrable, is this now automatically true? It depends on what?
On the region, R.
Well, the region R is this rectangle that we just talked about. You're tempted to say yes, right? You've given me an integral. I build it up as an iterated integral. I don't run into any problems along the way. I get a number. Great, I'm done. We always want to be aware of the hypotheses of our theorem. One of the important hypotheses of our theorem that we used, it was the first thing that we used when we started the proof, was that this integral exists. Now, is this integral existing equivalent to this integral existing, is the question. You may be tempted to say yes, but it turns out the answer is no. You may do the iterated integral, get a number, no problems, and it's not equal to the original integral over your rectangle because that just doesn't exist. If it doesn't exist, then everything we just did is nonsense because we started from the very first line assuming it exists. So let me give you an example. All right, so let me define this function as, and we're going to have to do something a little bit pathological to pull this off. But again, it's good to be aware that these things are out there. So I'll define this as 2xy if y is a rational number, and just as y otherwise. And let's say for x and y in this unit box. Okay, so let's do the iterated integral first of all. All right, so what do we need to do? We need to calculate this capital F. So let's compute capital F. There's two possibilities. Either we've put in a rational value or an irrational value. So if y is rational, then capital F is the integral from 0 to 1 of 2xy. All right, so that's x squared y. We plug in our limits for x, and we just get y. Okay, so when when y is rational, capital F works out to be this nice function. All right? I mean, we expect it to work out to be a nice function because for fixed y, this is a perfectly nice function. All right, similarly, if y is irrational, we expect a nice function. In this case, we're integrating the function y with respect to x. All right, well, we integrate with respect to x. That just gives us a 1, and this y is still floating around. And, oh, we happen to get y again. So although we started from kind of a very strange little f, a capital F is a very nice function. We're going to integrate this guy, no problem. So the integral of capital F is just the integral of y. And that is certainly an integral we can do. And we get a number. But I claim that that number that we got out does not coincide with this integral here, for the simple reason that this integral doesn't exist. So this is my claim. So what I'm going to do is just come up with a partition, or a sequence of partitions, on which the upper sums and the lower sums do not agree with each other at all. They're just far away from each other. And as you take limits, as you refine the partition, they just stay far away from each other. And that would show that the integral does not exist. So let's consider the uniform partition. So xi equals I times h, yj equals j times h, I and j are between 0 and n, which is 1 over h. And let's try to build some upper sums and lower sums. So for the upper sum, I need to take the supremum in each little subinterval. Well, in any given subinterval, right, y is going to dance infinitely many times between rational and irrational, right? We can always find a y value that gets arbitrarily close to yj and hits this value. We can also find a point that gets arbitrarily close to yj and hits this value, right? So the supremum of these is just going to be whichever of these is biggest. We may not hit that value exactly, it's not a maximum, but we'll get arbitrarily close to this. At some points, we'll get arbitrarily close to this. Okay, so which one is bigger? I guess which one is bigger depends on x, whether x is bigger than a half or less than 1/2. So if x is less than 1/2, this is going to be our supremum. Just grab this at the right endpoint. If x is bigger than 1/2, this one is bigger, and we have to grab this at the right endpoint. Okay, so I said if x is less than 1/2, then we want to grab y at the right endpoint. That's j times h. And otherwise, we need to grab the other one at the right endpoint. That's 2 times x. X at the farthest endpoint is IH. Y at the farthest endpoint is JH. Do you have a question, or are you happy? You're happy now. Okay, you looked unhappy for a moment. All right, and we do the same thing with the little m. But now we're trying to make things as small as possible. We'll grab these things at the left endpoint. I guess if x is less than 1/2, now it's this guy who's going to be as small as possible that we grab at the left endpoint. 2i minus 1, j minus 1, h squared. If I is, here, did I do this backwards? Okay, and then again, it'll be the other guy if I is bigger, if x is bigger than 1/2. Okay, so j minus 1h. Of course, you see the issue, the potential issue right away is that the capital M values are not probably that close to the little m values, right? These values may be quite different from these values. And that means when we start summing up these, there's no particular reason to expect we're going to get the same values as when we start summing up these. There's no particular reason to expect those to be close. And that's precisely the problem. So upper sum is the sum of all these big M's times volume of our little rectangles, which is 8 squared. And we've got to break this into two pieces, the I smaller piece and the I bigger piece. So this is going to be the sum from I equals 1 to n over 2. I think that this is less than, and this is a greater than or equal to. And this is less than plus 1. It doesn't really affect the final result in the limit, but just to try to be careful. All right, so what are we doing? We're summing from I equals 1 to n over 2, and all the j values of j times h times another h squared, so j times h cubed. And then we have to take all the rest of the I values. Okay, and for the rest of these, we get 2ij h squared. Okay, 2ij h squared times another h squared. Okay, once again, as always, there are formulas for this that you can pull out and use, right? This is the sum of the first n integers. This is just the sum of a bunch of constants, so it'll just be n over 2. Over here, things decouple, so we're summing over the first n integers and over the first n over 2 plus 1 integers. Okay, so at the end of the day, I'll spare you the details. At the end of the day, this comes out to something like this. And we can do exactly the same game with the lower sums, right? We have to split up our sum depending on which I values we're looking at. So pull out our same kind of formulas. But because summing rather different values, right? You know, these guys and these guys swap places, but that doesn't mean there's a symmetry that's going to give us the same values. This function is simply active in a different part of the domain, and it's going to have different values than this function does in the part of the domain it's active in. So this guy at the end of the day is 3/8 minus 5/8 h plus 1/4 h squared. But these are not particularly close together, right? If I look at the difference between them, well, usually I want my leading order term to cancel, but that doesn't happen here. So I'm left with a 1/4 plus something. And that's greater than or equal to 1/4. And as I refine my partition, as I let h get smaller and smaller and smaller, this still stubbornly stays bigger than 1/4. And that's not good, right? That is not the sign of an integrable function. An integrable function, we should always be able to make this less than any epsilon I like. I should be able to make this less than 1/8, for example, and I can't do it. So this then tells us that actually f is not integrable on our rectangle, even though the iterated integral exists and was easy to do. Okay, so that's my warning, is that as with any theorem, you have to know what the hypotheses are. And you don't get to use the theorem unless all the hypotheses hold. It's still a useful theorem because, again, we may have tricks for looking at an integral over a region and saying, oh yeah, I know this integral exists because the function is continuous, or maybe some other region, but that doesn't mean it's easy to do the integral. The iterated integral, once you know things exist, may be a much easier approach for actually evaluating, but you still have to know the thing you started with exists. Yes?
Is that continuous?
Which F? Capital F?
No, yeah, 2x, y,
This guy? This guy will not be continuous, no.
Is it piecewise continuous or not?
It is not piecewise continuous because you can't draw infinitely many continuous pieces. This is which is just going to be bouncing around infinitely often.
So if f is not continuous, can we say that it's not integral?
No, there are plenty of discontinuous functions that are integrable. A piecewise continuous function will be integrable, certainly. The problem here arose because it's discontinuous in a very pathological way. But no, discontinuous is not enough to say it's not integrable. Okay, we're not limited to rectangles. So Fubini's theorem that we just proved, we can pretty readily extend to other regions if we can kind of characterize them in a reasonable way. So for more general sets, well, let's be simple. Let's suppose that I have something that I can draw like this, where this curve and maybe the top on it. I'll go simple, but you can imagine from here getting more and more complicated, breaking your region up into a bunch of little chunks that each have this characterization and adding them up, right? So it doesn't mean your whole domain has to be this simple. And maybe here's A, here's B, here's C, and here's D. And this side I can somehow write as a function. And this side I can somehow write as a function. Okay, so this, I'm not writing y as a function of x here because y is not given by a function of x here. I'm doing this the other way around and saying x is a function of y here, which I can do. Right? If you turn on your head, it will look like a function problem. Okay, so I have my set that I want to integrate over. It's given by values x, y, such that, well, x lives between these two curves. Okay, and y has some bounds on it. And we have a function that's integrable on this set. We know that that is critically important. Okay, so we pick some A and B that enclose this. We're going to turn this into a rectangle. We have to turn it into a rectangle because Fubini's theorem we only proved on a rectangle. And we've done this before when we talked about regions. We said we know a lot about rectangles, so we just stick this in a box. I'm just going to do that again. Let's just choose some A and B. Okay, such that these are bounds on our U and V. Okay, so that gives me my rectangle. My rectangle is now AB cross CD. Okay, and we're going to do the usual thing to turn our region problem into a rectangle problem. We let our function be 0 out here. So let's define f sub s to be equal to our original function if we're in the region we care about, and 0 otherwise. All right, and we know that the integral of this function over the rectangle exists, because that's exactly how we defined the integral of this over S existing. Okay, so we know that the integral we started with is exactly the same as integrating this new function over R. But now we can use Fabini's theorem on this guy. So this, by Fabini's theorem, is integral over a rectangle of this guy. All right, as long as our component integral exists. So as long as we don't have any problems with this. Okay, so let's think about what this component guy would be. I probably should not be going from A to C here. Let's try A to B. All right, so let's see what that means. We're integrating from A to B. Well, in this part, I'm integrating the 0 function. Then I'm integrating my function, and then the 0 function again. So I'm going to just break this up. This guy is equal to the integral from A to u of y of 0 plus the integral from u to v. And here, this is the same as my original function. And then I need to keep going with my integral to b, and again, I'm integrating the 0 function. Okay, so this inner integral with respect to x really does take on this form. Okay, I can write it as the integral of my original function between the limits that I expect. Okay, and that means straight away I just have to stick in this second integral to get back to what I wanted. The integral of the function I care about over the region I care about, I get by doing the integral from c to d of this integral, which we said now has this form. Okay, so again, this is fully rigorously justified by Fubini's theorem. There's not extra work we have to do. And that's what's nice about a lot of this. Once we understand rectangles well, it's not that hard to generalize in principle. In practice is a different question. Once you start doing numerics and regions get weird. But in principle, the theory is not really harder for regions. Questions so far? Okay, so let's just do a couple examples that will feel easy and familiar, but now you can do these integrals with confidence, whereas in Calculus 3 you were always wondering if you were really justified in doing these integrals and if people were lying to you. Now we're going to do these with confidence. And if you weren't worried about that before, now going forward, whenever anyone tells you a theorem, you're going to be, or a trick, you're going to be worried that they're lying to you. So let's suppose we want to do this integral over this region. X is between -1 and 1, and y is less than or equal to 1 plus the absolute value of x. And we want to evaluate the integral of x plus y over this region. This function is continuous, so it's integrable, right? This function is continuous. This is not a pathological region, right? I mean, we can draw the region, but what was the key that we needed? The boundary has to have 0 content, okay? But this boundary is just made up of a finite number of nice curves, so no problem, right? We're justified in this. If I draw this region, let's see what we get. X is going from -1 to 1. Y is going from 0 to 1 plus the absolute value of x, so something like that. So here on this side, this is y equals 1 plus x. This is y equals 1 minus x. Once again, the boundary of this is just made up of a few straight lines, which is a perfectly well-behaved object in 2D that has 0 content. So note that x plus y is continuous, and boundary of S has no volume, so we're happy with this integral. And once we're happy that the integral exists, then we can start doing the iterated integral, and as long as we don't run into problems doing the iterated integral, we're good. We'll get the right answer. Okay, so the integral that we want is going to be, well, we probably want to do this in 2 pieces. We probably want to integrate over this left region and then add the integral over the right region. That's going to be the easiest way to break this up using Fubini's theorem for non-rectangles. And that's fine. We can do that. There's no problem with the integral over the whole region is equal to the sum of the individual integrals. And again, we haven't caused any craziness in the boundary. So we're happy. As long as we don't do anything bizarre, we're kind of in business. So the integral we want is, well, the left-hand side, x is going from -1 to 0. Y is going from 0 to 1 minus x. And then we do the same thing with the right-hand side. Right, and then we're just doing usual one-dimensional integrals using whatever tricks that we know, and we get some number coming out at the end of the day. We can use this for taking a hard iterated integral and turning it into an easy iterated integral. So this Fubini's theorem would also justify or tell us when we could swap order of limits. Okay, so let's say I give you this iterated integral. And you look at this and you're not very happy. Because something that involves an e to the x squared, something like that, you know that there's no elementary form for its antiderivative. So you say, well, can I swap the order of the limits somehow? Am I justified in doing this? Let me think about this a little bit. Can we write this as this iterated integral, can we relate it to the integral over a region? Well, if we were going to relate it to the integral over a region, let's see what that would look like. I guess we would have x going from 0 to 1. Oh, sorry, y going from 0 to 1. X is going from 0 to y. So here's the line, y equals x. So x is going from 0 to y. So if this is all hunky-dory, we would tend to relate this to this iterated integral to an integral over this region S. Well, that's fine. We can do that, right? Because this, although it doesn't look fun to integrate, it is a continuous function, right? This region, again, there's nothing wrong with this region. The boundary is just three straight line segments. So the boundary is well behaved. So we're perfectly well justified in saying, well, this is the same as the integral over this region. So then we ask ourselves, well, what if we tried to write this as a different iterated integral, where instead of having x go from 0 to y, maybe we took y going from x to 1. And we know from Calc 3, from all those sort of magic tricks I taught you in Calc 3, that changing the order of the limits of the integration can make life easier. So if we try it, well, what are we doing? We're going to let x go from 0 to 1. We're going to let y go from x to 1. Okay, again, there's no problem here. Continuous function, nice region. We're not going to create any kind of pathologies here. And now the inner integral is easy to do because there's no y that actually shows up there. So all of a sudden we have 0 to 1 of 1 minus x times e to the minus x minus 1 squared dx. And this is suddenly an integral that we're happier to do, right? Although it still has the quadratic up here in the exponential, it has the linear version of it, the same thing down here. So there's an easy substitution to make, and we're happy. So we do the integral, and we get a number. And we believe the number because Fubini's theorem has justified to us that we can do this. Because we have Fubini's theorem, and because we have something that's actually integrable over this region. I did these examples in 2D. This all works in higher dimensions, so I will just write down for you Fubini's theorem in Rn. The proof is not different than what we just did. There's just more things to keep track of. Okay, so here is the general Fubini's theorem. So let's suppose that f is defined on some rectangle. And this is integrable on R, where R is going to be a rectangle, I'm going to say in Rn plus m. So what I'm going to do is take my high dimensional rectangle and decompose it essentially into the cross product of two lower dimensional rectangles. That's what we did before. We took a 2D rectangle and wrote it as the cross product of one dimensional rectangles, intervals. Okay, so R equals Rx cross Ry, where Rx is a rectangle in Rn, and Ry is a rectangle in Rm. Okay, so what we're going to do is, instead of, or at least at the initial stage, instead of decomposing this into a bunch of single integrals, we're going to decompose this into 2 lower dimensional integrals. And then you could take each of those and continue to decompose them into lower and lower dimensions until you have a big, long, iterated integral over your full n plus m dimensional domain. Okay, so for each x in Rx, okay, so now these x are vectors. Okay, we're going to define our capital F. Okay, so let's just think of this as a function of y. Actually, let me write it like this. It takes the domain Ry. So f sub x of y is just our original function. Okay, I'm just taking the original function and writing it this way to make it clear that we're just now thinking of it as a function of the y variables, which are vectors. Now we suppose that this guy is integrable. Is integrable on Ry. Okay, and that lets us define the value of its integral. So the integral over Ry of f sub x of y dy. Okay, so I'm really just writing the Fubini's theorem we wrote before in 2 dimensions, where I've given different names to the intervals we had. I've replaced each of the intervals with these rectangles, but the theorem is not changing. And again, the proof is not changing. Okay, so from here, we can say that then A is integrable on Rx, and when we integrate it, we get what we want. So the integral of f over our original rectangle is precisely equal to the integral over Rx of this guy. And then we remember that, well, a of x really came from an integral too. So this is really the integral over Rx of the integral over Ry of f. And we've got this as an iterated integral. Right, and then once again, you could play the same trick with this integral over Ry. You say this is a high dimensional rectangle. Let's break it down into lower dimensional ones. Let's break this one down into lower dimensional ones. You keep going. And eventually you get a big string of single integrals potentially.